hear me? Yeah, good. So, okay, welcome. Again, my name is Antti Löytynoja, and I'm a senior application engineer at Mathworks. I've been with Mathworks more than 8 years. And in this talk, I will talk about how to implement predictive maintenance, again, in these different industries. And specifically, I'm going to talk about how you can enable, as an organization, to take better advantage of the domain experts, how to be more efficient in the different steps in developing predictive maintenance algorithms. But first, just a quick introduction to Mathworks. So we are an American company founded in 1984. We are headquartered close to Boston, originally founded in Stanford University, and we have about 20 international offices or so. In the Nordics, we have an office in Stockholm here. We also have a small office in Helsinki. And currently we are about close to 5,000 people and growing quite rapidly. So we are a software company, so we have some core products. So MATLAB is our core product, which is a platform for data analysis, data visualization, algorithm development, and deployment. And the point of MATLAB is that you gain insight quickly on a high-level language, using high-level language. Our second core product is Simulink, which is a platform for model-based design, designing and modeling multi-domain systems and verifying their behavior before you actually build any prototypes. And this usually involves automatically generating the control software for the system. And here are some of the companies that use our tools here in the Nordics. So with all these companies, we actually have some public references with. Are there any people in the audience who work for some of these companies? Okay, so some of you, maybe 20 or 30. Okay, so we all know that predictive maintenance, it's an application of data science and it's a multidisciplinary topic. And it requires lots of domain expertise, it requires a bit of computer science, and it requires mathematics in the form of machine learning, perhaps. And predictive maintenance is such area where perhaps the domain expertise is emphasized. So you need to know how the machines work, right? And many companies started doing predictive maintenance already, I don't know, 10 years ago, but that was usually driven by engineers. So the predictive maintenance wasn't on the board level. It wasn't a buzzword. And those programmers were usually quietly terminated, but now it's a hot topic again. Okay, so when you start some predictive maintenance programs, there are usually different individuals involved. So you have the domain expert, perhaps, and this could be a person who is doing simulations, CFD simulations, they do mechanical design, control design, and so on. And they have deep knowledge of how the machines work. But they might not have a PhD in machine learning. So they might have some idea how machine learning works, how to do data science, but they're not very proficient in that. And then we have some IT people who operationalize algorithms, maybe in the cloud environments, other systems. And it could be that these people own the data. And then you have the data science team who have strong knowledge in machine learning and data science, but again, they might have limited knowledge in the domain. And then we have a manager who comes and says that, okay, you need to implement a predictive maintenance service for our company. So how to do that? Well, obviously the manager can communicate with these different teams, they can assign tasks to these different individuals. But as you know, it requires a lot of communication between these different personas and teams. And that's not always straightforward. It's not always easy. And actually last year when I participated the Data Innovation Summit, which is another conference by Hyperight, and I was listening to a lot of presentations by data scientists, they were saying that the communication between the domain experts, that's difficult. Because these people talk CFD simulation, they speak controls, whereas the data science people, they talk machine learning and Python and stuff like that. So it's a little bit, there's a mismatch in skills. So the way we approach this problem at Mathworks is that we try to lower the barrier for the domain experts contribute more in developing data science applications, AI applications, and predictive maintenance applications. And to do that, or the way we do that is by providing tools that are easy to use, with which you can implement algorithms in a fast way. You can integrate whatever you produce, you can integrate with any systems in a flexible manner. And we provide a common platform for all the developers to do the work. So lowering the barrier for the domain experts to contribute. So we're not talking about replacing data scientists. They're very valuable. They're hard to find. What we mean is that domain experts, they have that valuable knowledge about the machines, and they should be able to contribute more in developing these services. And if you can enable them to contribute more, you're essentially boosting the innovation in your organization and taking advantage of that valuable knowledge that they have. Okay, so let's take a look at the different pieces in the algorithm development. So this is nothing new. So you start by acquiring data, you identify features, you train machine learning models, and then you operationalize them. And usually machine learning comes quite late in the process. And that's only one part of the process. Okay, so in the discussion, or in the topics that I'm going to talk about, I'm going to actually use an example. So we're going to look at an industrial heavy-duty pump. And this whole example is actually based on a real customer engagement that we did with Baker Hughes. So if you get access to the slides, you can actually take a look at the user story. So there's a link. So the examples are inspired by this engagement. So we're going to take a look at this pump, and pumps, as you know, they have sensors in them, they generate data. And for example, we could try to identify some failures by looking at the output pressure or volumetric flow from the pump. And in many cases, there are some failures in the pumps. You can commonly have 3 different types of failures. You could, for example, have some increased friction in the bearings or blocked inlets. And we sort of assume that, okay, those different failures, they leave a signature in the output pressure of the pump. But the point is that pumps, they have sensors, they generate data. So let's see and look at different key enablers that help you tackle some of the boxes in this workflow. So we're in the business of making things easy, so let's see how you can tackle some of these boxes with our tools. So one of the challenges that was actually mentioned many times during this day is that you have a lot of data. So if you, for example, take one of these pumps, and if there's a sensor in the pump, and there's a moderate sampling rate of 1 kilohertz, in a day you end up with 1.3 gigabytes of data. If you have more pumps, more sensors, you get more and more data, 78 gigabytes of data, for example. So you start to see the pattern, right? And already, as that was mentioned, so that translates to cost. So if your machines are operating in a remote location where you have to transmit the data through satellites, it's expensive. And if you're collecting all of that data, sending that data to cloud, and you're interested in finding some isolated events within all that data, it's a needle in a haystack problem. So how do you find those failures which might occur once or twice within terabytes of data? So the solution to that is nothing new, I would say. So you try to capture the relevant information in the raw data using some features, things like variance or mean values, skewness, kurtosis. And you hope that these parameters or features would capture the information that you're interested in using less data or with less data. But then you had questions. How do you extract these features? Well, you use signal processing, you use statistical methods. Which features should you extract? Now, this depends on the application, it depends on what kind of sensors you have, hardware, and so on. And that usually requires domain knowledge. So if your sensor happens to be a camera, you would use different types of features as with some one-dimensional signals, for example. And then how do you deal with streaming data? You have to worry about things like determining buffer sizes. You have to extract features over a moving buffer window and so on. So, but this idea is nothing new, but the way you do this could be different nowadays. So what you see here is actually pressure data from 240 pumps experiencing those different failures that I mentioned. And what you see here is basically an interactive tool that allows you to easily extract those features from the raw data that you have. So you basically see 240 signals plotted on top of each other, so we can quickly zoom into the data. And okay, we see some maybe anomalies here. So we see these downward spikes, and those could be an indication of a certain failure, but not much more than that. But with this tool, we can go ahead and extract quickly some industry standard features, things like variances, kurtosis, skewnesses. Click OK, and we calculate those features for all these signals. And note that we don't have to do any programming. And if you're in the business of, doing data science in the predictive maintenance area, you're probably familiar with these features. So now we capture those features with much less data. Obviously, we can also look at the data in the frequency domain. So there might be some spikes on different frequencies, and the locations and the heights of those peaks might be an indication of a certain failure, right? And of course, you can extract those locations and heights of the peaks automatically. So for example, we can say that let's extract maybe 2 most prominent peaks within a certain range of frequencies in the raw data. Click OK, and we calculate those features for all the data. So this is an easy way to calculate features. Extracting features is cheap, but once you have those features, you typically want to rank them somehow. You want to find out what are the features that really bring in some information. What are the features that help you discriminate, for example, different failures. So with the same tool, we can go ahead and estimate their importance. What are the most important features? Okay, so if you really want to avoid sending data from the device to cloud, you actually have to run the algorithm on the device itself. And if it's an embedded system, the unfortunate thing is that you can't run apps on the system. So you have to go to C or C++. So that means that you have to implement the algorithm in some other way. So what you see here is basically a simple MATLAB function that extracts those features that I extracted interactively a moment ago. So we go to frequency domain, we find the peaks, 1 line of command, we calculate those features, 1 single command for all those features. And if we want to translate this into C to run it on the edge device or on the embedded system, we can translate this automatically to C. And we can do that with an interactive tool, so we just need to provide the name of the function that we want to translate to C, give it some options. Do we want to generate source code, C or C++? Our target, is it an ARM processor or something else? And then we generate the code by clicking a button. And that will give you a C implementation of the high-level algorithm. So these tools exist so that engineers, they can develop the algorithms on a high level, and they can be a software engineer by pushing a button. So what did we discuss here? So you can use high-level language, you can use interactive apps. You don't have to do a lot of programming to get insight into the data and explore different ideas. And once you have an idea of the algorithm, you can write it down, and then you can automatically generate C or C++ code. And that means that you can reduce the amount of data because you do the feature extraction on the edge. You can react to changing conditions faster because you have a real-time algorithm. And again, you don't have to be a C programmer to do this. Right, so that was sort of the first parts of the workflow. So let's move into the fun part, so to speak, so machine learning part. So again, let's take a look at the pump again. So as I mentioned, there might be 3 different types of failures. And if we take all the different combinations of those failures, we might have 8 possible failure conditions. And we want to identify the failures by just looking at the output pressure with the features that we extracted from that. Now, let me go back to the tool that I showed you earlier. So we had identified the important features. So now we can go ahead and train a machine learning model. So the goal is to be able to identify the fault type, and that's essentially a classification problem that we can solve with machine learning. So what I can do is that I can maybe take some of the top features. I can send those to another interactive tool that guides me through the whole process of developing a machine learning algorithm. So I can select my predictors, I can select my response, and I can select my validation scheme, cross-validation or just hold-up validation. And then I can visualize my data or the features against each other, so I can maybe see if they separate themselves in the feature space. And this is the meat here. I can train all the classifiers available, all the popular classifiers, and see which one of those is the best one, which is the most accurate one. Because this is one of the challenges in machine learning. How do you find the best model? With this tool, you can train all of them and quickly see what's the best one. And then you can use standard validations, things like confusion matrices, to see how well does that model perform. And then you can export the model into MATLAB's workspace, or you can export something called a compact model, which you can translate into C. So you can put the classifier on the embedded device as well. All right, so let's take a look at a customer example who did something like this. So this is a user story from BMW. So they wanted to develop a classifier to detect oversteering. So as you can see, this is not per se an example for the predictive maintenance. But I think it's still a very powerful testimonial for apps and automatic code generation. So this team, they wanted to develop this classifier, and they were able to do that. They found a classifier that could detect oversteering with the accuracy of 98%. Good enough? And they used that classification learner app to do that. Furthermore, they automatically generated C code for that model. So they put that model into the car in just 3 weeks. So they went from an idea to an actual working prototype running in a car in 3 weeks. And what's noteworthy is that these were people who did not have formal training or education in machine learning. They had an idea what it means. They had some knowledge of how machine learning works, but with our tools, they were able to put this model and it worked on a car. Okay, well, sometimes you don't have the data. So this is already something that was discussed in the panel, in other sessions. So if you lack labeled data, if you don't have data for failures, how do you then develop your data-driven model if you don't have the data? Well, I have some good news. So if you're in the machine building industry, you definitely have some simulation models. The simulation models that are typically built for designing the system or the machine, they're usually generic. But what you can do is that you can take some sensor data from an actual physical asset, and you can use that data to fine-tune your generic model to be essentially a digital twin. And what you can then do is that you can model the failures, log the data from the simulation model, and use that data to develop your machine learning model. And that can be done by simply changing some parameter values in your simulation model. So for example, in this case, in the pump case, we were able to model a gradual blockage of the valve by simply reducing the opening of the valve in our simulation model gradually. Now oops, let me go back. And here's just a nice visualization of what a digital twin and the logged data might look like. All right, so let's then go on to the last bit of the workflow. So how to integrate and deploy the algorithms. So some of the challenges in predictive maintenance specifically is that you have different types of audience for your analytics or the results of your machine learning models. So you have to basically develop many different types of client applications. So the maintenance crews, they probably like some dashboards where they can see the operational status of individual machines. Operations teams, they're usually concerned with entire fleets and how the fleet is operating. And your customers may be interested in looking at different types of information. So you have to be able to deploy your analytics to different places. And what do you do then? Do you assign different tasks for 3 different software development teams? No, you don't do that. So if you have an application, an algorithm, what you can nowadays do is that you can take your application and you can package that as different types of software components, software libraries, Java, C#, Python, and so on. So with a click of a button, you can generate a software library that you can give to a developer and they can integrate that with other systems. The other approach is to actually go ahead and translate your algorithm into C or C++. And actually, we also support HDL for FPGAs and PLCs as well. And this essentially means that you can put the algorithm on the embedded device itself or the edge. And in many cases, you combine these approaches. So you put some parts of your algorithm onto the edge device, for example, the feature extraction, and then you send only the features to the machine learning model, which might be running in the cloud, wrapped as a Python library or whatever. But the most flexible way of deploying your algorithms is to expose that as a service, and you can do that. And that means that you have a scalable function as a service that can be consumed by any connected system, for example, through REST API. And we actually did this at Mathworks, so we built this demo where we had some edge devices sending continuously data. The data was sent to Azure, where the data was first ingested by Apache Kafka messaging system. So if you're in the IT, you probably know these things. Then the data was sent to MATLAB production server, where we had our models, machine learning models running to estimate remaining useful lifetime of the pumps and to estimate what was the component that was failing. And then the raw data was also sent to Elastic for long-term storage, and also the results that were coming out of the models, they were also saved in Elastic. Algorithms, they were developed in MATLAB. They were packaged as deployable archives and hosted on the MATLAB production server, which exposed those as a service. And then we also built some client applications, so dashboards using Kibana so that the operators could take a look at the operational status of the pumps and see what's the remaining useful lifetime or which component is failing. So this was done on Azure, but MATLAB actually supports different types of data sources, S3 buckets on Amazon, Azure Blob Storages, and so on. And if you want to deploy to different types of business systems, cloud services, you can do that with the help of MATLAB Production Server. And this essentially allows you to develop custom analytics for these dashboards like Power BI. So in the background, you run MATLAB, but your front end could be one of these dashboards, for example. So here are a couple of customer examples from the industries who used a couple of different deployment approaches. So Bosch, they developed a predictive maintenance algorithm for a push belt that they were developing, and they built this calculation tool in MATLAB, and they wanted to deploy this to different engineering teams globally within Bosch. And originally they deployed some standalone executables, but then they wanted to go in a centralized solution, so they used MATLAB Production Server. And that really helped them maintain the algorithms. SNCF, which is the railroad operator in France. They had a condition-based monitoring system for the rolling stock, and they developed some algorithms in MATLAB. And what they did is that they packaged some of the algorithms as a software library and simply integrated those algorithms without any manual coding to their existing system. Okay, a quick summary. So engineers, they have often a lot of deep knowledge about the assets. So make sure that their knowledge doesn't go unused. Enable them to produce software components, produce machine learning models, and so on. So we provide tools that help them easily develop algorithms using interactive apps, one-liner, language. You can generate code automatically, and then you can package algorithms to integrate with IT and OT systems. And also, if you're in the machine building industry, you probably have simulation models. So take advantage of those models, and if you're lacking the failure data, generate the failure data with the simulation models. Okay, so we have a booth outside, so if you want to see more how this works, so we have some demos for using digital twins to generate failure data, how to create condition indicators, how to develop predictive models for estimating remaining useful lifetime, and then how to generate code for embedded and edge systems. And that's all what I had. Thank you very much.
Thank you.